Our next session is going to explore some of the technical principles that underpin foundation models. And the first session, we talked a lot about foundation models in context of language, but I want to emphasize that the general idea of foundation models go well beyond language. And today, in this session, we'll hear some perspectives from people from vision, robotics, and theory. So we want to begin with our first keynote speaker is Yejin Choi. Yejin is the Brett Helsel Professor at the School of Computer Science and Engineering at University of Washington. She's also a senior research manager of the Allen Institute for AI. Her research interests include common sense reasoning, language grounding with vision, neural language generation. Her groups have built foundation models showing that they can be helpful in fake news detection, and more recently have been looking at how these models can be trained in a multimodal way. So Yejin, please share your screen and get started. Thank you.
Okay, so thanks much, Percy and Rishi and the rest of the organizers for the very timely and important workshop. I'm very excited to share my thoughts on the art of leaderboarding. Because these days, things are really entering this era of extreme scale neural models, I seem to get extreme questions, such as, are you sure we can't reach AGI by just scaling things up? GPT-3 is so magical. Is it even possible to do impactful research from academia without extreme scale compute? And I seem to have to answer these questions periodically these days. And given that many modern AI leaderboards became practically the battle of size of models and data and compute, it seems only appropriate to draw inspirations from such books as David and Goliath, The Underdogs, Misfits, and the Art of Battling Giants, or The Art of War, where the key takeaway messages boil down to know your enemy, choose your battles, and innovate your weapons. Of course, we need to interpret that for AI research, which I would interpret as evaluation with realism and scrutiny. And thinking of new, diverse, harder tasks and leaderboard design. And then finally, innovating our tools through smarter algorithms and more complex data. There's actually a lot to unpack here. And in this talk, I'm going to highlight 4 different flavors of potential research directions that might be fruitful, which includes interactions, multimodality, knowledge, and algorithms, all with this recurring theme of getting smaller models working better than potentially larger counterparts. So let's dive right in. The first part is going to be about language grounding through neurosymbolic interaction in a 3D world, which aims to address this old question of symbolic grounding problem. And so there's this award-winning paper that introduced octopus test, whether octopus listening in human communications in language can really figure things out, the world outside the ocean that they're living in. And so in order to answer that question, we could try placing an AI agent in a simulation environment. In this case, this is a Thor environment where the AI might try to make some cup of coffee and drop the mug and see what happens. Probably it will break and make a lot of mess in the kitchen. And so in order to do that, what we need to do is somehow changing our neural architecture to allow for learning from the physical interactions and learning the causal common sense knowledge in a physical environment. And at the same time, we also want to learn language, especially how to communicate the knowledge that it learned about the world, the physical world. So in order to do that, the quick idea behind our model is that at time t, we have access to the environment, such as maybe there was an egg at a room temperature. It's not yet cooked and it's broken. And at time t+1, maybe the egg becomes now cooked, temperature is hot, and so forth. So we merge this sort of a physical dynamics into the typical transformer architecture for learning language. I'm not going to go into the details here other than saying that the bottom half of the page corresponds to typical language model without the physical interactions, whereas the top part is about learning the action dynamics, the causal effects of any actions taken onto different objects in the environment. And so the result, quick highlight, is that, well, our model can do much better than T5, which is 100 times larger than the particular tiny model that we chose on purpose, just for the sake of argument that for reasoning about physical dynamics in the world, in the even simple world as Thor 3D environment, the larger models cannot always do well, even if provided with a lot of supervision data. And here's an example, qualitative example, what we're testing here. So for example, at time t, there was mug filled with water, and there was also sink also filled with water. And the robot comes in, empties the mug into the sink, in which case the sink is still filled with water, whereas mug is now empty, doesn't have liquid anymore. Well, super easy for humans to reason, easy for Piglet, our model as well, though T5 tends to go with the language bias. And if mug is empty, maybe sink is also empty. So it doesn't really learn the common sense understanding of how the world works, even if we provide with a lot of supervision data encoded as textual sequence to sequence format. So to summarize this part, one way to choose our battle is to test large scale models for causal common sense knowledge. Even simple common sense knowledge might be too hard for large scale neural language models that didn't have any access to the physical dynamics. And we demonstrated that we can perform better with much smaller data. But the problem with Thor or 3D environment in general is that whatever the engineer encoded is all that we have. So for example, if we want to learn richer common sense knowledge, script knowledge about the restaurants, which one of the examples introduced in our earlier work, visual common sense reasoning. Well, Thor environment doesn't support this. A lot of existing 3D environment doesn't support this. In order to learn when a customer is pointing to another customer when the server shows up, we know from our experience that this means that person being pointed to ordered a particular plate, but there's no way AI agent can figure this out just by interacting in an existing physical world in the 3D environment. So this is really script knowledge about broader knowledge about the events, event participants, why people do what they do, what sort of events happen in what sequence. And so it really goes back to this beginning of AI research that try to write down some rules and roles, event participants and preconditions and post-conditions. But turns out, although we know all this knowledge, it's not that easy to write this out at scale. So it didn't go too far, except that now that we have a lot of data, especially lots of YouTube videos that are perhaps underexplored, the question is, can we learn multimodal neural script knowledge at scale? In particular, at the time of submission, we had 6 million YouTube videos collected. If you were to watch this, not sleeping, not eating, you need multiple decades to finish them all as a person. So what can AI learn from watching lots of YouTube videos? Well, in addition to the fact that there are some correspondences between object names mentioned through language and some objects that you see in the video screenshots, it's also going to be able to learn bigger events that define what happens or what happens in the kitchen. So we work with video automatically transcribe the text. And so this person is explaining what he's doing. And as you can see, the space of language is much, much richer. And there's a lot of information beyond the literal content of images. And then there's this notion of time, which adds to the causal knowledge, because without time, there's no causality. There has to be always, between causes and effects, some time gap. So using this rich knowledge, we can then write a new learning objective that can incorporate unique strength of this data that goes beyond the still images or just raw text. We can, for example, think about unshuffling frames in order to learn higher order event knowledge. And so we were able to do this. And the quick takeaway summary of this approach is that we can learn a fair amount of temporal common sense knowledge to the point that we can sometimes do quite well, even on zero-shot cases. And we achieve a new SOTA on 13 different benchmarks that require some sort of visual, textual, and causal reasoning. And in some cases, we're winning over larger industry scale models. So also being in academia, we had only base size models successfully trained so far, but in some benchmarks, we are winning over a larger size model. And this power comes really from the complexity of information that's unique in YouTube videos. So next, let's think about another type of learning signal that I will refer to as knowledge, especially symbolic knowledge. In particular, I'm going to also talk about symbolic knowledge distillation, which will distill off-the-shelf neural language models to causal common sense models. So when people talk about knowledge distillation, we typically think about compressing larger language models to smaller language models. They're both supposed to do the same job. Whereas here we are changing the purpose of the larger model to do specialized operation, focusing on causal common sense reasoning. And in order to get there, though, I think I need to briefly share the context of this work. So my collaborators and I have been excited about this idea that language models are not knowledge models right away. We have to do something about the neural language models or neural models in general so that they become knowledge models. And so we studied symbolic common sense knowledge graph, known as atomic, as well as a neural common sense model or common sense transformers, known as COMET. And both COMET and atomic have a 2020 version that's ever bigger and better than before. And here I'm going to highlight, just in case you haven't seen what atomic looks like, it's a lot of if-then knowledge. So for example, if someone gets their car repaired, then we can infer that probably as a result, that person needs to pay the bill, might need to call Uber for a ride. Probably this person needs a mechanic and money beforehand. So we can reason about preconditions and post conditions, especially involving people's motivations and intents and emotions. And then we can also reason about physical entities, such as, what can you do with money? You could potentially pay for repairs, but also you could fold that into origami if you want it. And then we can also reason about counterfactual or event-to-event relations, including hindered by relation, which is basically counterfactual context in which an event cannot occur. So the car costs too much, then it's difficult to get it repaired, or I think it meant to repair cost too much, or the car is totaled completely. And so in our previous atomic versions, everything was crowdsourced because back then, which is very 2020, last year, it seemed that machines cannot do this reliably. And in fact, we trusted humans better. So we had 1.3 million such if-then common sense rules written down over 23 different relation types. And just in case some might wonder, how well does GPT-3 compares to COMET? To give you a bit of a sense of a perspective here, our COMET is more than 400 times smaller than GPT-3, which is not available to everyone. With that in mind, GPT-3 is much better than GPT-2. The jump in performance is really admirable. But since it's too large, not accessible to everyone, if you want to use something smaller and better, then COMET can do better. So this is higher the better, I should have mentioned. It's accuracy judged by humans for machine-generated common sense inferences. And so previously, this power of a COMET came from human annotated knowledge graph. Now the question is, can we bypass human annotation altogether, or more or less, I should say. So here comes this idea of a symbolic knowledge distillation. GPT-3 is too large. Can we somehow compress it down to something smaller? And oftentimes when we talk about knowledge distillation, we tend to face performance loss. But here we happen to have something even better. So first of all, we generated atomic 10x. Now it's 10 times bigger, at least with respect to a subset of atomic 2020 relations. And it's much better, much bigger, and it costed much less. And in fact, it's also more diverse, it turns out, than human-authored atomic. So atomic 10x seems very promising, but the question is, are they high quality? Because in our previous evaluation of GPT-3's capability of common sense, it was less than 80%. It was something like 73. Depending on how you measure it, it's a 70 something. So that's not good enough compared to human-authored common sense knowledge bases, which have 86.8% human agreement with other humans. By the way, common sense knowledge is always a little bit elusive, and there can be some disagreements among humans. And so it turns out, although we can find a lot more correct knowledge generated by GPT-3, the overall quality is not as good. But it turns out we can teach Roberta to tell apart or filter out potentially worse knowledge. And if we do so, then we can attain quality that we've never seen before, at least not when working with the crowd workers. Depending on how much we are willing to filter, we can reach quality accuracy as high as 96.5%. And this is still much larger than ever before compared to atomic 2020. Atomic 10x is much bigger. The green corresponds to the size. It turns out this better atomic also teaches better COMET. And so the blue bar shows the system performance, COMET performance on common sense inference on previously unseen events. And it can generalize much better than ever before, and certainly it's much better than GPT-3, at least on this task. So to summarize, with GPT-3, now we have new potential for distilling it down to smaller common sense models by using that for generating the knowledge graph on its own. And so for the first time, we have a machine-authored common sense knowledge graph that's better than human-authored one in all criteria: scale, accuracy, and diversity. Now, let me briefly highlight entirely different line of research that focus on inference time algorithms, because it turns out, depending on different reasoning tasks or leaderboards that we're targeting, Algorithms alone can make better lemonades out of off-the-shelf neural models. So here, the work is about neurologic decoding. And a lot of the times we resort to sequence models for anything that generates language as an output, machine translation and dialogue response generation and image captioning. But there are cases, new fun benchmarks such as CommonGen, where that recipe doesn't work very well. So the task is given a set of words. We have to use all the words and generate some sentence that's reasonable. Now, even with a very large amount of training data for fine-tuning supervised training, sequence-to-sequence models do not understand the logical constraints here, which is to use all the words given in the input. It learns to use some words in the input, but not necessarily all words. As a human, you do not need even a single example for this to fine-tune yourself on, because we just understand the logical constraints in a declarative manner, and we can operate with this right away. We have a similar issue with machine translation today, where some of the inflection rules, grammar rules can be violated, especially when the translation go against particular bias in language, such as gender bias. So to summarize, we have a lot of language generation problems in which at the decoding time, we need to deal with some sorts of logical constraints. In our work, we explored this through CNF form, conjunctive normal form. And this is basically a complex or convoluted search business, discrete search that I will just pass over. But the results were quite surprising to us, even for us. We had a hunch that this could work, but not this well. So here, the summary is that when you look at the coverage chart, so here the higher is the better, neurologic, whether supervised or zero shot or unsupervised, which are green and yellow, the constraint satisfaction coverage or ratio is near 100% all the time, regardless. The supervised approach using conventional beam search does better with larger models. So x-axis shows the size of the model, but it doesn't really fully learn the problem. And this is not, neurologic does not perform at the expense of the quality of language that it generates either, because Ruja Meteor in this task correlates well with the human judgments on the quality of the output. And here we see that unsupervised neurologic outperforms supervised approaches. Not only that, unsupervised neurologic on smaller networks outperform supervised approaches on larger networks. So we found similar patterns across different tasks that our paper investigates empirically. So
1 minute.
To summarize, the premise of this talk is that scaling laws are real, denial is futile. Really, among my all-time favorite papers include this scaling laws for oral regressive generative model. The previous one was good as well, but this one really was turning point for me as well. And also, I can't imagine research without GPT-3 to T5 clip. Roberta, sorry if I missed your favorite as well. However, I don't think we can get to AGI just by scaling things up, because scaling laws explain only a necessary condition, not the sufficient condition as a whole. And so about these earlier questions that I mentioned, well, first of all, self-driving cars were coming for several years, and I don't know if it's coming in a decade even. And even when we look at what appears to be solved task, where AI achieves a human level or superhuman level performances, the same task with a slightly different input, even though those input should be easy from human perspective, the AI could make miserable mistakes that no human would make. And so essentially we're solving on your data set without solving the underlying task properly. And so about this earlier question, can we even do impactful research from academia? Oh, yeah, totally. We just need to understand where the weaknesses are, and then think about the weaknesses really resulting from the current paradigm of deep learning, focusing too much on self-supervised learning on a lot of raw text, followed by supervision on a lot of exam problems. Now, this recipe is the winning recipe for a lot of leaderboards. However, not all leaderboards, in the sense that the moment the leaderboards test generative evaluation, where the model has to generate language output, there's a far gap between human and machine. And especially for tasks that requires logical constraints, we are very, very far. And the reason why it doesn't work is not necessarily because supervision itself is wrong. I think that there's something missing even from the foundation, which is self-supervised learning, in that as a human, we cannot really learn deep learning just by looking at a lot of Python code on our own. We really prefer taking a class or reading tutorials. And so humans learn much more effectively from declarative knowledge. And I think that's how AI might need to learn more efficiently as well. So to summarize, the art of leaderboarding, I think there's really a lot more strategies potentially possible than what are discussed in this talk. But really the limit is our own imagination and creative thinking. And the particular directions that I presented here aim to address diversifying learning signal, especially with emphasis on grounding, emphasis on the complexity of information, because I think that's really the gist of scaling laws. It's not just about the size, it's the complexity and diversity of the information that's inherent in the data, and emphasis on learning knowledge about the world, especially incorporating declarative knowledge, and then the importance of inference time algorithms. I think this is really underexplored, fruitful research direction that I'm excited to see more of. So I stop here and ready for questions.
All right, thank you, Yejin, for that wonderful talk. Really love the analogy there. So let's take some questions. So one question is that it's really great that you're able to show these improvements with smaller models. There is an element of still trying to push up on scale. For example, Comet is 400 million parameters, which is not exactly small. So what do you think of the role of scale? Is there a kind of a minimum scale that you need to do kind of meaningful research?
Yeah, I think still the larger, the better. So any of what I presented will work even better if someone puts even more compute, like especially inference time algorithms attached to larger models. Well, the gain might decrease. It may become more diminishing return, but always the larger is better in many cases. And I think that's because inherently, the larger models have seen more data. It's almost similar to how human researchers, we cannot get Nobel Prize just by reading a lot of papers, but it tends to correlate. If you read more papers, probably more ideas arise as well. So the diverse information is really important. I think the quantity of information, the complexity of information in the data is really critical. And ignoring all that, staying in a very tiny amount of data will not go very far, I believe.
Yeah, great. Another question from the audience. So data collection for these foundation models is a challenging issue. How do you collect the YouTube data given the express Google copyright not permitting downloads? This is a very specific question.
Yeah, so that we discussed quite heavily with lawyers on our end as well. And so the policy, I think, is probably debatable depending on where you're coming from, but we interpreted the fair use interpretation of it, though because of this thresholding on download, it took a very, 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 very long time for us to collect the data, like really very long time. This project was going on and on for more than a year, maybe more like 2 years. And we almost gave up, but we didn't, because we're too curious to see what happens if we tried on videos.
Yeah, good thing you didn't give up. All right, that's all the time we have. Thank you again, Yejin, for the talk and answering the questions. So now we will move on to 3 10-minute talks. We'll start with Chelsea Finn. Chelsea is an assistant professor of computer science and electrical engineering at Stanford. Her lab is interested in how robots and other agents can acquire broadly intelligent behavior through learning and interaction. And more recently, she's been looking at how offline data could really help improve the sample efficiency online. So Chelsea, go ahead and share your screen and take it away.
Thank you for the introduction, Percy. So I'll be talking about the role of foundation models in robotics. Great. So in particular, I'd like to start by emphasizing that unlike other applications of machine learning, robotics is an area where we've seen a lot less success in real-world scenarios. So in particular, this is a clip from, or several clips from the DARPA Robotics Challenge in 2019 that highlight some of the challenges that arise when you try to put robots into unknown environments. This challenge was ultimately considered a fairly clear failure because none of the robots were able to successfully complete all of the tasks. And I'd like to bring this up to specifically contrast it with a number of other areas of machine learning. For example, Google Translate, voice recognition, recommenders. We've seen pretty good functionality in the wild from these other machine learning technologies, unlike the kind of challenges we see in robotics. Also, in contrast, the DARPA Grand Challenge in 2005 was actually considered to be a big success in autonomous driving. And still today, we do not have autonomous cars in the real world. And so this just all goes to show that how challenging the robotics problem is. That said, it's not all failures. Robots can actually do some impressive things. So for example, here's a video of a robot that learned how to use a spatula to lift an object into a bowl, which is a fairly dexterous task. That video was from 2016. Here's also a video of a robot performing parkour from Boston Dynamics in 2001. And that said, there's a bit of a catch. So in both of these examples, the behaviors that were shown in these videos were manually tuned for this environment, or specific to the environment that they're in. So in the case of the Boston Dynamics video, the parameters of the behavior were tuned for that particular course. And if you change something about the course, the robot would fall flat. And likewise for the video on the left, this was actually using machine learning. So it was actually able to adapt to this environment, but the entirety of the system was trained on 15 minutes of data from that particular environment. And so if you change the position of the object, if you change the spatula, the robot would also fail. And so essentially where we're at in robotics is that we can allow robots to perform complex maneuvers, but only in narrow controlled environments. And so in particular, there's this grand challenge in robotics of trying to allow robots to generalize to in the wild environments. And I think that we're at a really exciting place right now because we've seen foundation models pre-trained on broad data be a fairly successful and promising recipe in other areas of machine learning when we care about generalization to open world settings. That said, there is a bit of a catch, which is that unlike in other areas of machine learning, we don't have tons of data that's lying around on the web. We're typically operating in a setting where we have minutes of very narrow data that we collected on our robot because it's fairly time consuming to run experiments with robotics. And so the key challenge is we need to move from minutes of narrow data to days or weeks or even more of much broader data. Just like how it doesn't take humans just minutes to learn how to walk, for example. We need much more data and broader data at that. And so to this end, there's a number of interesting questions towards addressing this challenge of data scalability in robotics. And at Stanford, we're working on a number of different of these questions. For example, whether robots can collect high quality data with minimal supervision. So for example, this work used weak supervision outside of the loop of data collection in order to allow the robot to explore its environment. We're also looking at questions like how we can leverage data across institutions and across different robot platforms so that, like the rest of machine learning, we can actually share data across labs and reuse data more frequently. We're also looking at questions like how we can leverage the data from the web, which may not contain a lot of robots in it, And also, once we have broader data sets, whether robots can learn from this broad data with minimal supervision. And this involves algorithms like self-supervised reinforcement learning. Now, in the rest of this talk, I'd like to just zone in on one of these questions and get into some of the details. In particular, we wanted to study whether robots can learn reward functions using in the wild human videos. And this is a really important problem because reward functions are essentially a prerequisite for getting a robot to learn behaviors in the first place. If you don't know what the success criterion is, then good luck trying to actually learn the behavior. And we want to use it in the wild videos because it may allow these reward functions to generalize much more broadly. So what the setup looks like is we have lots of videos of humans in many environments with many tasks, and a narrow amount of robot data that was relatively easy to collect because it was only in one environment, only with a few tasks. We want to combine these two data sources to learn a reward function that ultimately doesn't just perform well in a narrow setting, but can also generalize to unseen environments and unseen tasks. And for example, we might want to give a human demo, a human video of a new task in a new environment, allow the robot to learn a reward function from this video, and then ultimately have the robot actually solve that task using that reward function that can generalize to new tasks and new environments. Okay, so how do we actually go about trying to address this problem setting? Well, many of the ideas that scale are the simple ideas. So the idea that we use here is also quite simple. Basically, we're just taking two videos and learning a classifier that can output whether or not those two videos are performing the same task. And you can train this using human data, using robot data, and using a mix of the two. So for example, we'll pass in these two videos and train the model to output 1 because both these videos are closing a drawer. We'll also input these two videos and train it to output 0 because these are doing different tasks. And likewise, we can also give it pairs of human videos. And then once we have this classifier, we can use it as a reward function conditioned on a video of a human to tell the robot whether or not it's successfully completing the task. We refer to this as domain agnostic video discriminator, or DVD. And in simulation, importantly, we tested generalization not just to the training environment from which we had a narrow amount of data, but to new environments with new colors, a new camera viewpoint, and a new arrangement of objects. And we tested this on a variety of different tasks. And what we find is if we test generalization to new environments, if we only use narrow robot data, the performance isn't very good. But once we incorporate videos of humans into the data set, the performance improves by more than 20% when specifically looking at generalization to new environments. And in particular, this is an example of what that looks like, where we can pass in a video of a human, and the robot can use this to derive a reward function, which allows it to solve tasks not only in the original training environment, but also in a variety of other environments as well. Okay, and then we can also test generalization to new tasks as well. And again, here, similar to the environment generalization scenario, we also see a 20 to 30% improvement in performance when testing for this generalization. And finally, we tested this environment and task generalization on a real robot, where we trained on all of the diverse human videos that were in the something data set in combination with a narrow robot data set from this environment in these two training tasks. And when evaluating on new environments and new tasks, we see that we can essentially show the robot a video. It can use this to derive a reward function and then ultimately accomplish the task in this environment that the robot hasn't previously had. The reward function didn't see any data from this particular environment. Likewise, we can give it a video for another task, like pushing a tissue box to the left, and the robot can also figure out how to solve this task. And again, the reward function didn't see any robot data for either of these two tasks or in this environment. It leveraged the videos of humans from the web in order to generalize to these environments and these tasks. With that, I'd like to thank my students, especially Annie Chen and Suraj Nair, who led the work that I presented at the end, and happy to take questions during the Q&A period.
All right, thank you, Chelsea, for that interesting talk. Let's move on now to Tengyu Ma. So Tengyu is an assistant professor of computer science and statistics at Stanford. He investigates the theory of deep learning, reinforcement learning, robustness, non-convex optimization. And more recently, he's been looking at the theory of language models as well. So Tengyu, please go ahead and get started.
Okay, thanks, Percy. This is based on the section 4.10, the theory section of the report, whose lead author is Aditi Raghunathan, and also based on some recent papers with students of my group, Colin Wei, who is a rising fifth-year student doing some fantastic work on deep learning theory and theory for semi-supervised learning. So let me jump into the talk, which is on the possible theory of foundation models. So I guess let me start by talking about what we think would be the theory's role in studying foundation models. So ideally, as in many other engineering and science areas, we hope the theory could forecast outcomes of experiments and reduce the number of trials in the experimental process. In this context, it really means that you can save a lot of compute, which means you can save a lot of money and a lot of carbon emissions. And eventually, I hope the theory can guide technical decisions and inspire new methods. However, arguably, this list might be too ambitious for us for the theory in the current time. So the short-term goals are to formulate the problems, to analyze existing methods, and to explain observed phenomena. In some sense, in my opinion, these are necessary goals because if you don't understand existing methods, then you have to, it's kind of hard to inspire new methods. So these are what I'm going to talk about in the talk. So in my opinion, foundation models require some brand new theoretical techniques. And to demonstrate that, let's start by talking about what statistical learning theory, the standard one, can offer us. So in standard statistical learning theory, we train on some empirical loss, which is defined on some finite training data set. And then you evaluate on a population loss, which is defined on the population distribution or the infinite data setting. And the goal is to show that training on finite training data set suffices for us to test or perform well on population distribution. And the core is basically to show that these two loss functions are somewhat similar in some sense. And you can see that these two loss functions are indeed similar. It's the same task, the same loss function, the same model parameterization. The only difference is the p hat versus p. So basically, you have to show that the finite data set is a statistical approximation of the population distribution in some sense. However, for foundation models, the pipeline is much more complicated. So for example, in those methods with optimization-based adaptation methods like BERT, what you do is you train with the empirical pre-training loss, which is defined on some large unlabeled finite training data set. And the loss function, of course, also has to be unlabeled, for example, contrastive learning or multi-task language model loss. And then you adapt your parameters using an adaptation loss, which is defined on some downstream training data set, and also with some downstream labeled loss. And the parameters you adapted is also somewhat different from the pre-trained parameters. At least you need one linear head on top of it, and also you may train a subset of the pre-trained parameters. And then you evaluate on the population downstream distributions or the infinite data setting. So you can see that the challenges are that the theta and the gamma, the pre-trained parameter and adaptive parameters might be different. The pre-training distribution and the downstream distribution might be different. And also the loss function, the task between the pre-training and downstream setting are also different. One is unlabeled and the other is labeled. So our approach towards building a theoretical framework for analyzing this is to try to reduce to supervised learning as much as possible. So first of all, we see that between adaptation and evaluation, this can be kind of handled by standard supervised deep learning theory because the only difference is between D hat and D, and you mostly just have to show that D hat is an approximation of the population downstream distribution. And how do we bridge the gap between the other two boxes? So what I'm going to do is I'm going to introduce two more boxes to make the gap smaller and identify the most important issue in analyzing foundation model. So first of all, the pre-trained empirical loss probably should be similar to the population pre-trained loss because standard generalization theory. So you transfer from p hat to p. And second, on the right-hand side, standard statistical learning theory tells us that if the optimization can succeed, then you only have to show that there exists some gamma star, some parameter that can give you small adaptation loss on infinite data. You only have to show the existence to guarantee finally the algorithm can find such kind of like gamma star. So what we have abstracted away is the standard generalization between P and P hat and D hat. And also we have kind of hide or assume the success of optimization so that we don't have to worry about it. And what we focus on is the population case, and which is what we call pre-training adaptation interface. And here we only have to work on the population distribution, the infinite data setting, and we still have to deal with the distribution shift, the different tasks and loss functions, and the parametrizations between theta and gamma. So in some sense, this framework doesn't lose the essence of the problem and allows us to focus on the important aspect. And how do we establish this arrow? So far, we only have somewhat ad hoc techniques to show this based on the particular setting, the particular loss functions, and the particular data distribution, so on and so forth. I'm going to show two analyses, maybe in the interest of time, just one of them, for some concrete algorithms. And maybe in the future, we can modularize the proof further in the future. So I'm going to talk about contrastive learning briefly. So this is an algorithm that tries to learn representations by pushing representations of augmentations of the same image closer, and also pushing away optionally augmentations of the different images further away from each other. So in our language, this is a contrastive loss is the population, is the pre-training loss, and the adaptation loss is a classification loss with the adaptive parameter, which is the linear hat. And how do we bridge the gap between these two boxes? What we show is that if you have a small population pre-training loss, it means that your presentation has to have certain geometric structure. And the structure here is the distance between the representations has to capture certain kind of intrinsic distances between the examples, x and x prime. So what we're thinking is that we have like a manifold of examples, maybe a manifold of cat, a manifold of dog, and there are also submanifolds of breeds, different breeds, and the intrinsic distance is defined such that the distance between x and prime is close if x and x prime can be connected by a sequence of neighboring natural images. For example, suppose you have two French bulldogs here, which looks somewhat different, but we claim that they have small distance because they can be connected by a sequence of images and that are neighboring images, and each of these images is a natural image of French bulldog. On the other hand, suppose you have a bulldog versus a Burman cat, then we claim that the distance is large because you cannot really connect the bulldog with a cat with a sequence of natural images. In this sequence, it must be some place where you have a kind of a half dog and half cat, which doesn't look very natural. I guess in the interest of time, I'm going to skip the second example, which is about language models plus prompt tuning. This is about the NLP setting, and we have to make different assumptions. And for example, we have to make a generative model assumptions on the data distribution, and we have to do some different approach. In the future, we hope that some of these analyses can be unified. And also, let me briefly mention that this framework is only is explicit or implicit used in many analysis. We only kind of like summarize this framework from the existing work. We didn't propose them ourselves, and it has been used in the past many times. Looking ahead, I think there are many technical challenges, especially for theoreticians. For example, we need to have proper and realistic assumptions on the population distribution. We need to have more mathematical tools to deal with these population distributions and characterize the internal workings of the models. As you see in a contrastive learning case, we have to characterize the what the representations, the geometric structure of the representations to build this link between the two boxes. And we also need toy cases for debugging tools and comparing bounds. And another open question is we don't really know how to have a framework for in-context learning. The framework we presented only works for those optimization-based adaptation method. For in-context learning, you have a different mechanisms which seems to require different theoretical analysis. And finally, I guess the final goal would be to have some theory that can help with inspiring new methods in the future. We don't really achieve there yet, but I think it's possible in the near future. For example, in the contrastive learning paper, we did have a new contrastive laws, which is driven by the theory, which have provable guarantees. And it turns out that the contrastive laws is comparable to the SOTA and doesn't require large batch training as well. So this is not something super impressive right now so far, but hopefully in one day we can have better theory that leads to better methods in the future. Thanks for listening.
Okay, thanks, Tengyu. Let us move on to the third and final talk of the session. So joining us is Tatsu Hashimoto. Tatsu is an assistant professor of computer science at Stanford. His research uses tools from statistics to make machine learning more robust and reliable. And he also works on language model generation and evaluation. Tatsu, the floor is yours.
Okay, great. Welcome, everybody. I'm Tatsu Hashimoto, and I'll be speaking about some recent work by myself and my student Tengyu Zhang on understanding the inductive bias of language modeling and why language models learn to capture interesting structures such as syntax. Large language models and foundation models more generally have had an enormous and almost unavoidable influence. They have been behind some of the biggest gains in benchmark performance in NLP, and their use is ubiquitous in a range of downstream tasks. Shown here is performance on the SQuad 2.0 question answering benchmark. And the marked red gap is the large jump in performance attributable to the use of BERT. There's a clear inflection point in performance when these models began to be used. More intriguingly, careful investigation into these models have revealed that they seem to learn useful linguistic structures, such as dependency parse structures, without explicit supervision about syntax. Shown here in the top is undirected arcs from dependency parses in black, and colored lines indicating arcs estimated by a linear classifier or a probe trained on the internal representation of BERT, a language model. It's surprising that simple and task agnostic supervision in language modeling leads to these kinds of emergent and useful structures. Recent investigations have further shown that it is easy for these models to learn syntactic structures compared to others. The example shown here suggests that we can learn with near perfect accuracy syntactic probing tasks with only tens of thousands of examples, shown here on the left, but these same representations seem to fail on reasoning tasks regardless of the number of samples on the right. And this is consistent with some of the things that Yejin was talking about earlier in this session today. This is a bit of a mystery. Task-agnostic self-supervision seems to encourage language models to naturally learn some types of structures, but not others. What do we know about this sort of interesting mystery? On one hand, there's a large literature in NLP on probing tasks that try to understand what types of structures are embedded inside the representation of these large language models. And we have a decent understanding of the information that is contained in these representations and the complexity of the probes that is required to extract them. On the other hand, recent advances in theoretical understanding of language modeling have characterized the conditions in which pre-training can provably recover certain latent structures. And this was covered a little bit by Tengyu's talk, such as recovering latent variables in fill-in-the-blank tasks, or recovering hidden Markov models via language modeling. There is, however, a gap in our understanding when trying to explain the observed empirical phenomena from before using these theories. We know what structures are learned by language models, and we know what types of toy models language models can capture, but we do not yet understand why language models seem to naturally learn certain structures, such as syntactic parse trees, from what is essentially task-agnostic supervision. As a starting point, we can think a bit about what is sort of a common framework in theory characterization for these models, which I'll call the closed hypothesis. In this hypothesis, language models acquire representations that are useful for downstream tasks because language models are trained to fill in the blank, and filling in the blank can sometimes directly provide supervision for downstream tasks. So let me give an example. In sentiment classification, we might have a case where the model has to fill in, I mask this movie. Clearly, our ability to fill in the mask is closely related to our ability to understand the sentiment of the rest of the review. Because of the direct link between the downstream task and the language modeling problem, this is fairly straightforward to analyze, and there is now well-established theory for studying these types of situations. However, this doesn't necessarily explain the actual behavior of language model training, because the vast majority of masking problems have nothing to do with a specific downstream task. As an example, we might mask out the word the in the sentiment example, in which case we get no supervision for any downstream task. It is these more generic masks that are more likely providing the inductive bias in structures identified by probing studies. Is there a way for us to understand how much of the gains of language models come from task-specific masks, as suggested by this closed hypothesis, and how much of the gains that we see come from these random masks? We can answer this question with a simple and well-controlled experiment. If we restrict ourselves to tasks such as sentiment classification, we can come up with 3 different ways to train language models. On the left, we can train models purely on closed-like masks, where we identify sentiment words using a lexicon, mask those out, and ask the language model to fill them back in. On the right side, we can consider the other extreme, where we remove all these closed-like masks and only consider masking generic words. Finally, we can compare the performance of these 2 extremes to random masks that are used to train language models in practice. So what does performance actually look like? Since we don't actually have the computational ability to train these models from scratch, we can use a more computationally efficient way to run this experiment called continued pre-training. And we updated a basic BERT model on 3 types of masks across 3 different tasks. Vanilla indicates the performance without any of this continued pre-training. And we see that using closed-like masks in red gives huge gains. This is expected and goes along with the established theory. What happens with masks that are not closed-like? We actually find that even after removing closed-like masks, we see almost 50% of the gains due to pre-trained performance remain. This is really surprising because we explicitly removed task-specific supervision, but still got gains on downstream tasks. Even more surprisingly, we find that there's almost no difference in performance between randomly masking tokens and the no closed masks where we explicitly remove direct supervision about the task. What this suggests is that masked language modeling works not because of the closed reduction, but because there's useful signal beyond direct fill-in-the-blank supervision. So what's missing in our understanding of masked language modeling? So to try to understand this, we knew that we had to understand how generic masks worked. And we looked towards other algorithms which also rely upon fill-in-the-blank style prediction tasks and to understand these connections. One major class of algorithms that rely on fill-in-the-blank prediction problems is the classic graphical model structure estimation problem. For example, the CMIT algorithm for estimating conditional independences in a graphical model consists of repeated tests of whether pairs of variables can be reconstructed given the remaining ones. This is basically a masking task. And the connection here is pretty direct. BERT-type language modeling seeks to mask some tokens and fill it in as a way to learn representations that are useful for predicting relationships among tokens. CMIT-style graphical model structure estimation algorithms seek to mask variables and reconstruct it as a way to see whether there is strong dependence among the variables. This brings us back to the high-level point. Masked language modeling is naturally designed to learn statistical dependencies among token positions in a sentence. We've shown this formally in recent work, and I'll refer you to our paper for full details, but I want to describe the high-level connection. First, since a masked language model gives the probability distribution over masked tokens, a language model implicitly estimates the dependence between any 2 tokens. Here, we're going to write this down as this I hat object here. What we can show is that the model's estimate of dependence and the true dependence must be similar, as long as the masked language model achieves low loss. More precisely, if a language model has low log loss on the fill-in-the-blank task, which is the term on the right of this inequality, then this log loss upper bounds the approximation error between the language model's internal estimate of conditional mutual information and the true population conditional mutual information on the left of this inequality. Thus, common masking objectives serve as a surrogate upper bound to learning statistical dependence. This is all nice, but why do we care? Let's return to our opening question. Why do masked language models seem to learn syntactic structure so naturally? We might hypothesize that it is because these models are learning a different type of dependence among tokens, statistical dependence. And this is a testable hypothesis of the theory. If this is true, then we should be able to first recover statistical dependencies learned by large language models like BERT, and then we can use these dependencies to construct a parse tree, and then finally we can evaluate this whole procedure as an unsupervised dependency parser. It turns out that literally just using conditional mutual information that is estimated in BERT serves as a reasonably good unsupervised dependency parser, even outperforming the classic DMV algorithm from Klein and Manning. Even nicer is the observation that minor changes to the type of statistical dependence that we measure seems to decrease performance, and that the type of dependence being implicitly measured by BERT is actually the best out of those that are plausible to try. This is a somewhat surprising finding from the empirical perspective as well. it was widely considered that mutual information alone could not serve as a dependency parser, and this low performance PMI baseline shown here was considered and ruled out in the original Pine and Manning paper. It is a nice side effect that studying the theory of mass language modeling leads to an empirical observation that certain types of statistical dependence do relate closely to dependency parse trees. To wrap up, there's 3 key points to this talk. First, I want to pose an open problem and a call to action. We have very little understanding of the inductive bias of language models and why these models naturally learn some structures and not others. Second, we proposed one way to answer this via statistical dependence estimation, but of course, this is likely just the tip of the iceberg. Lastly, this hypothesis led to an interesting validation and finding that statistical dependences in mass language modeling directly encode syntax. It's also encouraging to see that there's been recent work, such as PMI masking from AI21, that demonstrates these mutual information-based approaches can lead to improvements in language model training as well. Thank you, and I'm happy to take any questions in the Q&A.
All right, thanks, Tatsu. Now I will invite Tatsu, Tengyu, and Chelsea back on stage, and we can do some questions. So maybe I can start out with one question is, I think of theory is most useful when it's kind of making broad source predictions about things that you can't do experiments with, when what's possible or not. And we're in a situation, Chelsea mentioned how foundation models, we want to really use it for robotics, but we're not really sure what's possible. Is there anything that we can say? Is there a theory that can tell us how successful foundation models would be for robotics?
I guess, maybe not yet so far, or maybe not directly so far, but I guess as we progress, hopefully you can probably, for example, one thing that the theory could say is to predict how likely the adaptive models can generalize. So maybe that could help to decide how many training examples you need, how many samples or trials you need, so on and so forth. I guess Chelsea knows more robotics more. I don't know too much about robotics.
I mean, regarding robotics specifically, I do think that there is a reason to believe that it might require more data than typical supervised learning scenarios, because you have a sequential decision-making problem where your actions can affect the state of the world in a very tight feedback loop. And this means that there are so many different possible outcomes that your robot might find itself in, so many possible situations. And as a result, you may need more data to try to better cover that realm of possibilities. And so, I mean, I think that we don't have that much theory on even the supervised learning scenario, but I think that it's very likely possible that any sort of results in the supervised learning scenario might require even more data in the robotic scenario.
Right. Go ahead, Tatsu.
But on the flip side, that's a promising sign, because it seems like foundation models, like from the robustness section of the white paper in some sense, like they have provided some of the most promising general purpose robustness interventions compared to like some of the other things that have been tried. So if the issue is changing environments, it does actually seem like this may be a very promising direction.
Yeah, it seems like a big challenge throughout is bridging the gap between the pre-training distribution and the kind of the task distribution. We've seen some theory about, Tengyu, it's kind of the centerpiece of theoretical analysis. Tatsu talked about how, the gap between the task and the mask language model. Is there, I guess, on the flip side, I guess we often think about robustness as kind of a problem in, let's say, in robotics, because we want, especially if with physical systems, for things to be robust and reliable. So maybe this is kind of continuing on Tatsu's point. Is this synergistic? Is using foundation models make it, on one hand, we don't know how to think about the gap. On the other hand, we think that foundation models helps us bridge this gap.
I think part of the issue is it's very unclear what types of assumptions are appropriate. Like if you look at the landscape of theory papers, there's sort of these latent variable based methods. There's also some of the contrastive learning, like latent model recovery style methods for like topic models. And it's not clear at all what problem structures real world data follows. And so we can come up with great explanations for why things work and how we're bridging these gaps. But like, I think Tengyu's point, I think is good, is it's not clear which of those factors that we're modeling is actually impactful for any of these tasks. And I think that's a huge challenge that I don't know if there's even a roadmap to solve.
Maybe I can ask more specifically. So this idea of contrastive learning kind of shows up, right, in Chelsea's setting where you're classifying two images of same task or not. And I guess that's one objective. And there's, on the other extreme, there's kind of autoregressive language modeling where you're just modeling everything. And BERT, maybe masked language modeling is somewhere in between. Do we have any sort of insights, theoretical or empirical, about what are the strengths and weaknesses of each of these? Is it a matter of compute, or does it depend on the domain?
I guess I can say some kind of like internal guess I have about the differences between these two. So at least, if you believe in analysis that we have about contrastive learning, you can see that it heavily depends on the notion of class in some sense, or subclasses. And also it really relies on how do you design the augmentation, the positive pairs. So in some sense, it only captures those things that are captured in the positive pairs. And if you're, for example, in language, I suspect that the masked language model is stronger than contrastive learning because you can capture other aspects that cannot be captured by the designed, handcrafted augmentations that you do in the language, if you are going to do contrastive learning for language modeling.
I think that it probably also depends on the downstream task. In the work that I presented, we only needed to, for reward functions, you don't need to understand everything about the world. You just need to understand whether the video is showing the desired task or not. And so you can potentially throw away a lot of information. Whereas if you actually move towards trying to control the environment and try to actually act and learn behavior, then you end up needing a lot more than that. And we've actually done some work on learning these sorts of autoregressive models, except of video, of generating video, rather than of text, which is the typical language modeling case. And one empirical challenge that we ran into is these models just simply underfitting. I think that we probably need much larger models when we move from text to images and try to apply these same kinds of models. And which is rather unfortunate for all the reasons why larger models in language are unfortunate, but it at the same time, it does suggest that the successes in language may also translate to that once we do actually figure out how to scale those models.
I also think I think we don't necessarily have a full understanding of especially the empirical performance trade-offs between the different masking objectives. Like if we look back at history, right? GPT-1 came in, it was autoregressive. And then people switched to BERT style like masking, or like went to Elmo and then BERT style masking, which was ever less autoregressive. But now with GPT-3, people are realizing that like prompt-based methods can now sort of like extract a lot more information out of these autoregressive models. I think the jury's still out on what the right contrastive loss or like self-supervision loss is until we sort of figure out also the right fine-tuning and like the right representation extraction strategies in addition to training.
I wanted to maybe ask about, prompting and kind of this close. So Tatsu's talked about how there's the representations that you get from kind of masked language modeling, and then there's the kind of more explicit close reductions where maybe the objective is the thing that you actually want to solve. And I wonder if that is kind of language specific, or whether there's analogs in vision, or is vision more about kind of just learning the right representations? Is language somehow special in that there's this kind of prompting and close behavior, or there's something more general here?
I think it's in the language case, the prompt can be the label itself, which I think is maybe unique. But in vision, there's also these sorts of infilling objectives, which are very, very similar to masking. And in fact, like Jason Lee's paper on analyzing these kinds of like fill in the blank style supervision, like does these kinds of vision experiments. And so I think the supervision itself is not unique at all, but whether there's something special about using the label as the target mask, I think is a different question.
I also don't think that it's necessarily specific to language. I think that you could imagine a scenario where a robot is acting in the world and collecting data. It does something, and then it sees that a human is unhappy, or it makes an unhappy face, or maybe the human says something. And if we actually have robots operating in those environments, then it's basically the same as the language case, where we just want to essentially get the outcome where the human is happy, or whatever we're optimizing for. And so it may not be all that different, although at the same time, we might be quite far away from robots operating environments in which humans are in and so forth.
Actually, one thing that could be interesting here is that, a lot of vision tasks are kind of associating a higher level semantic label with, an image. I guess there's segmentation of the 3D reconstruction. But in robotics, you could argue that the ultimate output is the control, which is now back in the kind of the space of, it's almost like you can just do language modeling in some sense. Now, of course, there's the problem that you don't observe the control signals sent to humans or robots, perhaps, and you only get weak supervision. But I wonder if that can be a powerful metaphor and analogy that helps us think about autoregressive language modeling just on things that happen in the world.
Yeah, and typically when we train these video prediction models, we do actually condition on the actions that the robot takes. And when we have robot data, typically we have both the observations as well as the controls that the robot took. And that is really, incorporating those controls into the system is really critical for actually learning the behavior, as you might imagine.
All right. Let's see if there's any other audience questions. Maybe we'll just wrap up now. So I would like to thank the presenters, Chelsea, Tatsu, and Tengyu once more. And that concludes the talk portion of the session. Thank you. All right, next, I would like to invite Chris Manning to moderate our next panel. Chris is the Thomas M. Siebel Professor in Machine Learning and Professor of Linguistics and Computer Science at Stanford. He also serves as Associate Director at the HI. His influence on the field of NLP, I think, is pretty hard to beat with his famous textbook and his early work in driving deep learning and NLP. So welcome, Chris, and take it away.
Thank you, Percy. And in turn, then I'd be delighted to have the panelists join us for this second panel session on technological foundations. So if all the panelists would like to join and turn on their video now, that would be great. Okay, so I have 5 panelists to introduce. But, I thought maybe what I could do is introduce people in pairs and then have them answer a question as we go along. So, this is going to be tricky because how can you introduce 5 people in pairs? So I thought I could clone Natalie and have her be in part of 2 pairs, but we'll get to that in a minute. So maybe the first pair of people I can introduce is, so first of all, there's Sanjeev Arora, who's the Charles C. Fitzmaurice Professor of Computer Science at Princeton University and has been a really prominent contributor to work on theoretical models of machine learning. And then there's Natalie Schluter, who's both a senior research scientist at Google Brain and an associate professor of computer science at the IT University of Copenhagen. So I thought I could maybe first start by asking the pair of you. I think it's fair to say that the dominant strategy we're seeing at the moment, perhaps especially in industry, is that if you build these models big enough, amazing capabilities will emerge. And so I was hoping to get your thoughts on whether that seems a workable strategy that will keep powering us for the next 5 years, or do you think that there are important theoretical questions that really need to be worked out to continue making progress? Like, how can we make use of theoretical and mathematical tools to give us a better understanding and drive further progress?
Maybe I'll take a stab first. Yeah, firstly, I want to say this has been a great event. I've been listening to the amazing talks and discussions all day. Fantastic. So I guess about this question, is big enough all we need? I'm guessing that we need more capabilities in the model. At this point, these models are a little bit reminiscent of the Vannevar Bush Memex machine, storing all the world's knowledge. It seems feasible at this point that they could do it, but then to reason about it, that's the open question. So we probably need new ideas there, like probably some measure of knowledge other than cross-entropy loss for prediction, because the goal, after all, is to do this kind of reasoning later on. So some kind of test of reasoning, maybe. And probably better training algorithms and better architectures. I mean, those also probably need some more work. Over to you, Natalie.
Yeah, so I think maybe it's funny that you ask us too this question, because I think like for us too, it's kind of the opposite of maybe what the trend is in NLP right now, which is just build the systems and just see what happens. And it's kind of a really different way to approach I think like traditional computer science or mathematics, where it's more like in biology and medicine, where you kind of put stuff together, or in experimental physics, you put stuff together, you see what happens in the end, and you take some observations down. And I think the difference is that when you are doing this in biology or in medicine, and you're actually thinking about making stuff for humans or making stuff for living beings, that there is some sort of protocol that you have to follow to ensure that you're not harming them. So I don't think that you can just bash some stuff together, see that there's some good progress, and then release a medicine onto the world. You actually have to follow some very careful situations, very careful experimentation to make sure that you're not doing some harm. And I think that our field hasn't quite realized that there is this parallel. There's this switch in working, and there's this parallel that we have to recognize, and we have to observe like other parts of science do. But so I could talk about this for ages, but you might want to.
Okay, maybe pull out the first answer and go on. So let me introduce another two of our panelists. So Kavita Bala is the Dean of the N.S. Bowes College of Computing and Information Science at Cornell University, and Jitendra Malik is the Arthur J. Chick Professor of Electrical Engineering and Computer Science at the University of California, Berkeley. So both of you, I think, are primarily vision people, or at any rate, primarily interested in the physical world. And so maybe you could both start by sort of saying something about the importance of the physical world, vision, sensory grounding, sensory motor grounding, to pursuit of AI, and to what extent foundation models are lacking that, and whether it can be addressed. Do you want to go first, Kavita?
Sure. Jitendra, do you want to go, or I'm happy to go?
I can go as you wish. We can toss a coin.
Well, we maybe go back and forth a little bit. So this is a great question. So first, I have actually been enjoying also watching the workshop. So thank you for organizing this. I'll say I've struggled a lot with this question of where physics sits. And I'll say Jitendra sits on the vision learning boundary. I'm in the graphics and vision boundary. So I sit very much, and I come from the graphics tradition. And we in graphics have spent a lot of decades getting the physics right on things. And so and actually Percy said it this morning. He started off saying he was a skeptic, but then these new foundation models have made him question, that, the time has come, a paradigm is changing. And I admit I also sit in that space, but I go back and forth and I'll explain some of my quandary. So one is I do think these foundation models are fascinating. There is a lot of opportunity for them to achieve many of the things that maybe in the past we would think that you would need a physics engine for, let's say. So, they can produce a lot of the generation aspect, producing the level of realism with DALL-E, et cetera, is just astounding, the kind of output that they can produce. So when I first started, I always used to think there's a place for physics. Then I see the kind of output that comes with this. And I think, wow, where is the place for physics? And I'll say there's still room for a place for physics in at least two places. Actually, three places maybe. First is you want to simulate. And so the physics engine is the one that produces all the data maybe that you can use. Your real world situations aren't going to give you enough data, so you can use it for simulation. But the bigger issue is every time in computer graphics, when we found that we tried to fake something, controlling the output is very, very hard. You can produce something very plausible that fools people a lot of the times. And then when you want to actually control it to get to a particular output, that's very hard to do. And that's where you actually, if you look at the movie industry, they actually go back to simulating the physics right from first principles rather than doing approximations, because it's so much easier and cleaner if you actually understand the physics. So that's another place where I think physics plays a role. And finally, in inverse graphics, when you're actually trying to understand what goes into the world, we have these differentiable rendering engines now. There's room for them actually to help you understand what's going on in the world. And it's hard to fake that without having the real physics in there. So I think there's room for physics in all of these places, but I'll turn it over to Jitendra and get his input.
Yeah, so I think I'm going to take a more directly critical role. If not from the point of view that these models are not playing a very useful role in machine translation and speech recognition and a lot of sort of language tasks, and I grant them that. I want to take a very strongly critical role when we're talking about them as the foundation of AI. In fact, I think the term foundation is horribly wrong. These models are really castles in the air. They have no foundation whatsoever. What is the foundation of intelligence? We can take an evolutionary view. Okay, 500 million years ago, Cambrian era explosion, you have animals that can move and that can see. And it's the sensory motor loop which develops the basics of intelligence in insects and all the way through mammals and so forth. Okay, 5 million years ago, we can talk about manipulation, the hand, the importance of that. And then maybe in the last million years, we can talk about language. Or you can take the life of a single individual. We can take a baby from birth. What is the baby initially doing? It is seeing, it's putting things into its mouth, it's touching, it's doing multimodal interactions, it's doing experiments in the world. That's what Alison Gopnik calls the child, the scientist in the crib. And through those interactions, experiments, observations, it builds up a model of the physics of the world. What happens to objects when they fall? What happens when somebody shouts at another person? Social interactions, et cetera, et cetera. On top of that, at some stage, language comes in. So language is added on top of an individual who's very embodied, interacting with this sensory motor world. Now, at some point, the child goes to school and then reads books. And at that point, doesn't have to look up the meaning of words, can figure out meaning from the context of other words in a sentence, and then Wikipedia and so on and so forth. So there is a role for language. My colleague Alyosha Afros would say that we should stay away from language for the foreseeable future and developing language AI, but I'm not so extreme. There is a role for language, but this language is on top of this sensory motor entity. Like 90% of intelligence is there in a dog or a cat. That is what we need. So the language that we have right now in these models is not grounded. I mean, we know something from 30 years ago. There are these papers on this stuff. This is like going back to ELIZA or something like that. There is this fakeness here. There is no real understanding. And I think that this needs to be recognized and called out. I want to commend Yejin, because at least there's one person I can see in the language community who sees this, and I liked her talk very much because she was calling out the need for sensory.
Jitendra, maybe we should wrap up there for the intro. There's clearly more to talk about on that topic.
We need to build a foundation. It needs to be grounded in sensory motor.
Yeah. Okay, thank you. But we'll get back to that. So finally, let me introduce the fifth panelist. So if you were around for the talk earlier, you saw Yejin talk. So Yejin Choi is the Brett Helsel Professor at the Paul G. Allen School of Computer Science and Engineering at the University of Washington, and also Senior Research Manager at the Allen Institute for AI. So for my third question, I will have a straight language question. And although both Natalie and Yejin do multiple different things, I will count you as the two language people. And so let me ask a sort of a question about language. So with the recent models like GPT-3, there's evolved this way of doing fine-tuning, if you want to call it that, or few-shot learning, where you're simply giving a prompt to a huge language model, that you're giving it some text and that then drives its behavior. I mean, what do you think about that? I mean, you could think that this is just a horrible hack, or you could think, this is brilliant because now we're moving to a world where we can control the behavior of these models by talking to them, just the same as we can get human beings to do different things by talking to them. Maybe Yejin first, then Natalie.
I'm sort of itching to respond to Jitendra's
leave that till afterwards. We can do that next after the intros.
I focus on the more imminent question to answer. So I love it. The fact that we could probe GPT-3, what it knows and what it doesn't know through language. And I think this is really, really important going forward for the following reason. I think it really increases the expressiveness of our interfacing mechanisms with learned models, because language is the thing that we do understand as human. We cannot understand anything else as well. Whenever we develop some new labeling schemes or new logical forms to describe some meaning to the machine, then we have to teach ourselves that symbolic mechanism, which almost always not as expressive as natural language. And I think going forward, maybe we could even do that more with vision models as well, in the sense that the way we understand what vision models know or not know, say clip model or DALL-E, language is really convenient there as well, because it allows us to explain or describe a lot of complex things beyond just categories of things, objects and actions.
Yeah, I mean, this raises a couple really interesting points. So one point follows from what Yejin was saying, which is, I mean, if these models are capable of, like, you know, solving problems that actually we as scientists haven't been able to decipher ourselves and give the instructions to a machine to do, then can we actually learn from the models themselves how to actually structure the different tasks? What do they consist of? How do you get this performance without actually us knowing what to say to the machine to do? But on the other hand, I think it's really interesting that you can get these models to do a variety of different things, but then I am more interested in how these models are approximating a lot of different tasks at the same time without actually telling them precisely what to do. So, you know, picking apart these things and finding out what the mechanics are. Maybe these are two sides of the same coin.
Okay, thank you. And so now we'll move on to sort of the more general part of the panel, I think I'll turn immediately back to this issue of grounding, because that was raising a lot of passion. But in general, so for the panelists, feel free to jump in if you have something to say. But equally, if you want to, under the sort of reactions button down the bottom, there is a raise hand. So if you want to raise your hand to signal that you do want to get a chance to speak, I can also help make sure that you have one. And then for people who are watching this, we're happy to get questions from the online audience as well. So do feel free to enter them in the Slido interface that's available online, and we'll see what we can get to. But let me get back to foundation models and grounding. So, I'll be quite frank. There's a rich history of how we came up with the name foundation models, but it has had bimodal response. Some people have said positive things about it, and some people have said very anti things about it. But, one of the reasons why we chose the name was our feeling was that the same general kinds of techniques of using self-supervised style learning over extremely large amounts of data, which was pioneered in the language realm with models like GPT-3, would spread to other modalities, and people would be doing exactly the same thing with vision models, with models in robotics. And so we wanted to think of foundation models as not something that was language specific, but in general referred to using a huge amount of world knowledge that you were slurping up from the environment around you. Normally it's a model given data, actually. And out of that, using self-supervised style learning techniques, you could learn a general foundational base of knowledge, which you could then apply to particular tasks. And so it wasn't meant to be all about language. And so, I agree, and I presume everyone on the panel would agree that grounding and the physical world is super important, even as me as the most singularly language person. So, if I perhaps start again with Kavita, Jitendra, do you think there are prospects for using the same kind of techniques of simple self-supervised learning tasks in other modalities and sensory fields, for touch and vision, to build the same kind of general purpose foundation that you'll then be able to use to better understand the world around it?
Can I?
Sure.
No. Yes to self-supervision, but not in the way that language models work. Okay, let's start by building a dog. What do you need is, you need knowledge of physics. You need knowledge of how objects interact. You need knowledge of social physics, how agents interact. So what is very important is physical simulation. So yes, I believe in self-supervision, but the self-supervision comes from the fact that we live in a three-dimensional world with which we interact. And we interact with objects. A child pokes at something and that something falls. That is self-supervised learning. But this is a very different self-supervised learning than doing the closed task in natural language. But through a collection of those experiments and interactions and observation, so some of it we do actively, some of it we observe, that is how we build the substrate for intelligence, and that's how insects do it, and that's how dogs do it, and that's how primates do it, and that's how humans do it. On top of it, language provides a communication ability, and it transcends various barriers because we can talk about things which are not there and so forth. There are these so-called 11 things which are special about language. And I don't want to detract from the role of language, but language without grounding, go back and read about Helen Keller. Helen Keller was, the process of how she was taught about the real world was very interesting, and how she learned to speak. It had to start with grounding. It doesn't have to be vision. I won't be a vision chauvinist. It could be audio, it could be touch. But some grounding through perception of the real world is central. Kavita, to you.
Well, not surprisingly, I kind of agree that you do have to have that interaction as the part that you build on. That's sort of our foundation that we build on. So that's the direction from which we come to it. And I do agree that that's sort of, but I do see a path for using that to build up to the kinds of models. They're rich and they can simulate. I mean, there is a generation part that is incredibly powerful in what these things have learned. But as I said, I think you get into this uncanny valley mode at some point. You actually need to get the rest of it to be able to understand what you've actually learned.
Oh, okay. Well, maybe next to Sanjeev to award putting his hand up, and then after that, maybe hear from Yejin her thoughts.
Yeah, I mean, I wasn't sure either what foundation referred to. At the first idea I had was this was some kind of an Asimov joke or something. But you know, I think I did interpret it fairly broadly, as you said, and you know, all the things that are in these models already allow them to, in principle, learn in the way that Jitendra is asking. You know, with attention, you can easily modify the input or the stimulus and see what happens, right? And try to predict what happens and see if that happens. So yeah, I guess I'm you know, it does seem to have enough capabilities to do the kinds of things Jitendra is asking for, syntactically.
Okay. Gee, I said Yejin and then Natalie. Yejin.
All right. So I think I agree and disagree with Jitendra about the importance of interaction and grounding. In that, totally agree with you that both interaction and grounding are important, but you know, language being grabbing more attention in the recent models such as Clip and DALL-E, and insisting on following the evolutionary route. I don't think that's actually fair blame on language in the following sense. I think there are two problems. One is that both interaction and the grounding can be purely language as well. From especially NLP perspective, we consider even social grounding. You know, there can be other kinds of grounding of the meaning of a language as well. And then, speaking of which, interaction can also be purely linguistic or language-based as well. In fact, GPT-3 is in some sense interacting with us, but not in the ideal way, in that it's not asking us questions in natural language about what it doesn't know. But I would love to see a future research direction in which the AI agent can actually ask questions and seek information with more agency than how it's taught today, which is to give a stream of randomly ordered text. And you know, as a human, we cannot learn that way either. We cannot just watch text and videos in the order of a sequence given to us without having the opportunity to ask questions. So I think interaction is missing there, grounding is missing there. Language may not be the key culprit there. There may be broader range of interaction and grounding that we are missing. Another aspect to this, in my mind, about the perceptual grounding is the challenge of robot and 3D simulation environments, because they tend to be fairly limiting. And I don't know, in my lifetime, I will see a robot or 3D environment that really matches the complexity of babies' experiences, let alone grown-ups. So we might be, in the meanwhile, looking for shortcuts for bootstrapping learning through language. And at the end of the day, I learned about tiger, for example, only by reading about tiger, not actually being eaten by a tiger or seeing somebody being eaten by a tiger. But I believe, I read about tiger in text, and I believe that they are scary beings. And you know, I can even imagine visually how it might look if it were to attack somebody. Similarly, let's just say, okay, tiger may be an extreme example, even like chewing on an apple. that juicy, crunchy feel. I don't think we can build a robot or 3D environment in which the reward signal is actually equivalent to the experience that humans have. So this is just impossible dream to have, that AI agent can have the same experience as humans do. And so when faced with that, it seems that whether we do perceptual grounding or not, and how well we could do in it, it seems that we also have to figure out another route through which AI can cheat a lot of knowledge by digesting a broader range of data. And that's one thing AI can be very good at.
Okay, maybe I'd better go on at that point and give Natalie a chance to say some thoughts.
Yeah, so I think so it is quite an important topic and a very popular topic that people are talking about, like with language grounding. I mean, there's other modes of communication that are completely ignored at text level as well. And I guess we also have to take into consideration that, well, babies actually can't read. So like what can you do as an adult by just reading? There's this interesting theory, linguistic theory, that posits that you can actually reduce the meaning of words to a very small group of primitive meanings. And that by combining this very tiny group of primitive meanings, primitive words, that you can cover all of the vocabulary of a language. And I'm wondering if, rather than this really broad question about grounding, because like, well, how much grounding? We're grounding here, grounding, what is the limit? What do you actually need? Is there a small amount, finite amount of interactions that are required to be covered in order to have like the foundation for language, or is it just infinite as well?
Okay. So a little procedural change. Actually, the production team would prefer that we don't use hand raising. So I guess we'll have to work on people jumping in with comments. But let me sort of continue a bit more on this issue of the sort of human learning. So, there's no doubt at all human learning is normal human learning. There's a complete range of sensors and grounding in this physical world. And even in cases where kids don't get the complete range of experience, there's still very much this grounded world. And so that's super important. And part of that Jitendra was starting to touch on was actually also interaction, that it seems that children only really learn successfully when they're actually learning themselves interactively, as the scientist in the crib, that you don't successfully learn by watching TV shows. And so both of those are clearly very important to how humans learn, and there's certainly things that we want to be sensitive to. But, on the other hand, it's kind of amazing how successful that this learning from a pile of data learning has actually been. So whether it's how much about language you can learn from something like a BERT or a GPT-3 model, or even like for some of the work that Yejin was showing, where you take a huge amount of YouTube videos, you can learn an enormous amount about the human world and how things operate. So, I mean, in some sense, because it's easy to do, that form of learning has been much more productive for advancing AI, I think, than people who've been trying to do grounded learning. So I guess the question I wonder is, can we ride this horse further? Can we, keep on working for another 3 or 4 years and leave worrying about grounding interaction for later? Jitendra. Sam.
Yeah, I want to say one good thing about this class of models, where I, having expressed my critique, would like to use them, is in multimodality. So vision does blend into into cognition, and vision does connect with language. And in the conceptual world, I mean, these transformer architectures are a very nice way to bring together different kinds of different representations, different kinds of information, knowledge, modalities, sound and text and images. So that's my one checkpoint in the favor of what you said. My negative will be, I actually feel that the world of sort of physical simulation and learning from video is actually making a lot of progress. I mean, I have devoted my energies to this in the last few years, and I think we are making great headway, and we are going to get good models for vision and robotics and connecting into cognition as well that way. Then I want to conclude with asking you a question, all you language types. Do you believe that these GPT-3 type models, how will they help you with chatbots? So the reason I'm saying I'm picking on chatbots is because I think dialogue is a central aspect of human language, right? It's not just lectures, we communicate, we talk, I ask Yejin a question, she replies back. We have this communication. After a while, both of us have a mental model of each other. There are these postulates of conversation and so forth, going back to Grice and so forth. Okay, do GPT-3, will you be able to build really intelligent conversation agents with GPT-3 type models? And if so, please show them to me. And I'm asking you in your world of language, whether you believe that will happen. I will take my answer off the air, as they say.
Well, I think I'm not meant to answer questions, so maybe one of the other three people who've worked on language would like to have a go at that one.
Just a clarifying question. So, Jitendra, by these kinds of models, you are assuming like the masking is done at random points or something, like you're just predicting what's already there.
Yeah. To be concrete, take something like GPT-3, and I want to convert that into a conversation agent so that we could have a dialogue for like half an hour on on some topic. And how would, as opposed to generating text following a prompt, for which these systems do a pretty impressive job.
I could answer at some point.
Go for it.
Though it seems I cannot type in the chat box that I want to respond. Chat is disabled. But anyways, so no, absolutely not. In fact, it's so fun pulling bad examples from GPT-3 Da Vinci, if about chatbot. Indeed, it's harder on GPT-3 because people-to-people, like regular conversation, probably doesn't exist as a large amount in internet data, but also because it's lacking mental models, it's lacking theory of the minds, and it's also lacking common sense understanding about social interactions and whatnot. So the fact that we root for language, though, doesn't mean that we are against knowledge models or theory of mind models. We can still work on all of these wonderful things through language as well. But I'm also into grounding. So I'm not against the grounding. It's just that there's limitation to how much we can ground depending on what sort of a grounding we are doing.
No, so great. I mean, thank you for saying this. So because that is part of language understanding, this ability to have mental models of other people, this ability to have explicit knowledge of the old style variety, scripts and knowledge graphs and so on. And I'm arguing that this obsession with GPT-3 means that you're ignoring some of those old ideas, which are, I think, very important.
Right. So the common sense transformers that I introduced earlier, people started using it for improving dialogue systems as well. Other people beyond our group started using it in order to improve the sig-to-sig models that cannot really say sensible things. Adding common sense model on top doesn't necessarily make all the conversation perfect yet, because this is something that came out only 2 years ago, and 2 years is too short to solve a major challenge. But I think it may be a potentially fruitful research direction to pursue further.
So actually,
I wanted to make one other.
I think Kavita wanted to go first.
Sorry?
I think Kavita wanted to go first.
Actually, I wanted to follow up on that. Actually, as a non-language person, it would be great when we're talking about these models to actually understand what the realm of application we think really is, because we don't think it's everything, and certainly not in the current state, right? They don't explain what they're doing. There's no understanding of why they produce a certain output. It's pretty random, and people know that they can play around with it and get, pretty crazy outputs. So it'll be good to actually, and I think you Chris, you started saying, are there theoretical properties, but theoretical properties even feels sort of more, we're pretty far from that. We're talking about very broad brush, maybe properties of what it can and cannot do at a very high level, that you can prune out a whole bunch of areas that we just don't think it's going to address, not in the current form in which it's approaching it, versus those where it is, right? Unless you add a little more thought in, more understanding into it, it's just not going to get there. So it'll be good to have people comment on that aspect too.
Yeah. You going, Sanjeev?
Yeah, so I think one thing that may clarify a little bit is, that the way, humans have the famous paucity of stimulus, right? Especially for language and many things. So their mode of learning may be different. And we know classically, in even simple settings, query-based learning can be more efficient, exponentially more efficient than just distributional learning. So I think the interesting thing from a theory viewpoint is just that you can do so much learning GPT-3 style from just passive examination of data. So yeah, this doesn't mean that maybe the query mode isn't important, but what is surprising is that you can get so far.
So maybe I should move on and ask about a question that someone in the audience was asking about improving our technological foundation. So we seem to be in this world where this idea of having prediction of mass stuff, most commonly a word, with the transformer-based model is sort of the new normal, right? That it's everywhere in language, and it seems to be increasingly spreading through vision as well. So the question is, what should we be thinking about for improving our architectures for the future? How is that architecture not capturing the kind of ideas like grounding that people are arguing is so important? Any thoughts? This is a hard one.
So I think there are a couple things that we have to be really careful about, and this is kind of related to some comments that I had before. One thing is security and privacy, really making sure that these models aren't not only copying and remembering information that they shouldn't do just from like a security point of view, but also like an ethical one. Since they're not able to determine whether what they're learning, the information that they're learning from is actually ethical information, or not racist, not misogynist, etc. These are also big spaces that we need to still work on today, like ethical computations that we do really easily every day as humans. Just even being sounding human, like sounding cohesive from 3 sentences ago to 2 sentences later. This is a problem as well.
Right. I guess the question is there things that we should be doing kind of architecturally to improve that? I mean, like if I sort of push back slightly on the cohesiveness one, it seems like if you compare GPT-2 and GPT-3, GPT-3 is way more cohesive. Like it will seem cohesive for multiple sentences at a time. So do we need an architectural change, or do we just need to pour in more data and stir?
Or more memory?
I would vote for architecture change. data change as well as architecture change. But what I mean by data change is that not just the raw data. Right now, we rely just on raw data, but we could rely on raw data plus knowledge graphs, plus maybe other means of QA interactions. As far as architecture goes, I feel like the current architecture is just so convenient right now, and we don't have any better idea. But my wishful thought, if I may just say something completely ungrounded, is that we need a model that can actually abstract away, summarize, and then learn some knowledge from its past experiences. Almost like from episodic experiences, we need a model that can learn semantic knowledge about the world, the semantic memory. So humans have apparently different memory architecture that says procedural memory is different from declarative memory, which is the memory that's describable through language. And under the declarative memory, there's episodic memory and then semantic memory. And these two things are different, and then they really interrelate in the way they operate and stored. Right now, it seems that we just have one blob of parameters that represent all of the above, which is a problem.
I'd like to follow up on Yejin's point. So this is one good way to think about it, these different kinds of memories. So the kind of knowledge, so the knowledge of how to bicycle or knowledge of how to walk is not of the same type as the one which is in these models. I wanted to build a little bit on what Natalie said, and this is something which is like a serious concern to me. We went from supervised knowledge to supervised training to unsupervised training, and we thought that's a good thing. But going with the unsupervised training was also the aspect of uncurated data. So the data which is being thrown into these things is uncurated, which means that it brings in a whole lot of crap. Basically, misinformation, disinformation, stereotypes. They will all say that doctors are male and nurses are female. They probably believe that Trump is the president of the United States. They probably believe that vaccines will cause chips to be implanted in your bloodstream, right? So all this stuff, because it's all there on the web, it is all there in these quote sources of knowledge, and to me, this is actually very scary. Okay, I'm sure there are other talks which will concentrate on the scary part, but as a purely scientific question, I feel that this is why that notion of scientific understanding is important. Whereas when we do a physics experiment, I mean, that is God's own truth, or maybe it's Newton's own truth. Okay, whereas something that some idiot has typed in and we suck it in, and then we regard that as a source of knowledge on COVID vaccines. I mean, okay, I end there.
Well, let me push a little further as to how people should react to that for the sort of technological foundations which you're officially being grouped under. I mean, so in recent years, there's been a lot more talk about socio-technical systems. Something I learned the other week was actually the term socio-technical systems was first coined in a study of English coal miners 80 years ago. So it goes to show there has been interest in socio-technical systems further back than you might think. So maybe we should be talking about socio-technological foundations. I mean, what can we be doing in terms of ideas of interpretability, avoiding reproducing private data and other things? Can we be taking steps that would build any of the properties that we'd like into the technical base of the models that we're building?
this is a huge topic, of course. There are so many pieces to it. I'll just talk about one piece, understanding sort of the provenance of where you're learning, tracking that as you're learning. And it's very hard to do with the amount of data we have. But the provenance aspect is something that I think we recognize as important, but we have not made much progress on. And it is something that matters. As Jitendra says, there's a mixed bag. And of course, at some point, you might arrive at a place where there are genuinely two alternate belief systems that are in conflict with each other, which I think is true for the world that we are in right now. And at that point, there's a question of, how do you actually even reconcile those? But you actually have to include that in how you come up with the output. You have to think about both tracking the provenance and recognizing maybe there's at least two worldviews, and together that arrives at maybe different outputs. And that's something that we need to integrate into how we build these models.
One thing that strikes me about GPT type models is that you can query with a prompt, which means this is what you should think about. It doesn't seem to be as easy to tell it to forget something or not to use something, which you can do with a human. So some kind of an orthogonal subspace of the prompt, if that made sense. Yeah. So that would be interesting, like to edit what it's learned.
So maybe not perfect solution toward that yet, but some of the unsupervised inference time algorithms, including work from our own group, try to address that issue to some degree. To some degree, meaning, for example, if it's about to generate toxic language biased against underrepresented groups, then we can try to undo the harm by having toxic expert talking down on the kind of words that toxic language model wants to generate. And we can also do this more in a hard constraint manner as well through, for example, neurologic decoding, in which we could have hard constraints not to talk about certain lexical items, although that would be a crude measure. But going forward, it seems that based off from some of the earlier comments from Kavita and Jitendra and also Natalie about the scariness of what GPT-3 learns from raw data. It strikes me that humans develop so much, we invest so much into learning material for teaching humans. And in fact, depending on the quality of learning material, students can learn drastically differently. Whereas we may not be investing as much into high quality training data or high quality knowledge that's guaranteed to be truthful. So it seems that maybe we're over investing into machine learning algorithms and try to find the magic answer just through algorithms when without the data, without not just the raw data, but also curated knowledge that's guaranteed to be true. We don't seem to be able to just somehow create GPT-4 magic that's ethically all correct and fact-checked.
So, I mean, I think there are interesting ideas there, but I think there's still this question of how we actually sort of have models that implement them, right? So human beings have this sense of information they've heard from different people, and they're sort of able to keep track of that so that they don't just blurt out things that they happen to hear some politician saying on TV without any sense of context. And then we've also got some sense of the world changing so that we know some of the things that we heard years ago might not be true anymore. Whereas at present, none of these models, whether just the language ones like GPT-3 or the more vision-y ones like DALL-E or Clip or something, they don't have any of that. I mean, can we start to build that into our models?
Yeah, in the future, I hope. But I think the key is knowledge. We cannot not worry about knowledge anymore when the AI models learn so well from raw data without correct knowledge.
Okay, you said yep, but how can we possibly do it?
Actually working on knowledge model as a thing. And study how to integrate that into language understanding or any neural understanding and generation models.
I was going to say that maybe focusing on having the model generate better explanations, because I think the saliency methods are probably not a good match for this kind of model. And I haven't seen a lot of work saying they are. And there's various reasons why, like, use of multiplication as an attention is actually very problematic for current saliency methods, because the saliency is just, weights to the input, pieces of the input, which is a very poor explanation in general. So maybe focusing on how the model can explain why it's doing something or think something, some explicit mechanism inside the architecture might help with all of these.
Okay, Jitendra, you had a comment?
Yeah. So I think that we should revisit some of the classical ideas which go back to sort of logic and conversational postulates and so forth, going back to 60s and 70s. I mean, so logic, right? There is some nice properties of logic, right? That logic is normative. And probability theory has the same characteristic that with certain axioms, it says this is what correct inference is about. So in those days, we used to talk about normative theories, and then it carried into the database world where they talk about curation and then being consistent and all of that. And now we've gone, and then those are normative theories, and now what we have is our descriptive approaches. So they are basically sucking up whatever is out there and then spitting it back at you, with no notion of of imposing sort of normative standards. So maybe you can say, yes, this is democracy at its best or worst, right? But I somehow don't like it. I actually now am going back to I started as a student of John McCarthy like 40 years ago. And for McCarthy, why logic was so important was because that was the one correct way to reason. And there are versions of probability which have the same characteristic. And we have given that up. Okay. So therefore we can have now you could say that's good because that enables us to store inconsistencies which will happen. But have we given up way too much?
Yeah. Well, that can maybe lead into the last topic. So before we run out of time, we should have a little bit on evaluation. I mean, the importance of evaluation was something Yejin mentioned in her talk. But among the questions that we've got, one closer to what Jitendra was just talking about, is how can we develop tests that better differentiate between memorization from intelligence in the sense of being able to reason? But I think as well as that, I mean, I think we want a lot more by evaluation, because we also want to be able to evaluate our models for issues such as bias or for what effects that they have in the world when we look at things like recommendation systems. So what kinds of evaluations should we be building that we don't yet have that will allow us to better interrogate these models? Who's game to try that first? Yejin, Natalie?
Sure. I was just trying to see if others might want to chime in first, but no, I love to talk about this. So I think we need a leaderboard, because everybody who has a model wants to climb leaderboards on ethical judgments like biases and toxicity and all that. So that even people who don't care and who think there's no problem, they're not biased, there's no serious bias against racism or sexism. Because by working on this research area, I learned that actually a lot of people in our field genuinely think that there's no problem. Some of them don't. It's just they don't talk about it too publicly about it. But I think we need really a leaderboard for that sort of problems as well, so that that line of research gets a lot more support, or research activities as well. And something else I want to emphasize is generative evaluation, or evaluation that makes the model to generate an answer as opposed to choosing which of the 4 choices might be the correct one when one of them is guaranteed to be true. Because the problem with the multiple choice question is that there's always a superior dataset biases that are in the data that sneak in somehow. And we end up measuring how well the model can effectively fine-tune without actually being able to solve the underlying task in a natural way. That in the open world setting, for example, there's no oracle that can provide us with 4 magical choices to choose from. So
okay, great. And maybe we should get thoughts from others on evaluation.
So I agree with Yejin. Of course, like our field would advance so much if we could have leaderboards for all of the neglected topics that we think should be pushed forward. I think we fall on the same sort of problems that like our boring old metrics already have, is that they don't really cover the performance the way we quality of performance the way we actually would like them to. And so I think it's really difficult to have a metric that can give you a good understanding of like what an empathetic person would say is acceptable with output of a system. So yeah, working on empathetic systems that of course would be very, very interesting, but I don't see how to not have a human in the loop and not ask Black people if this is offensive, but have a Black person metric instead, for example.
Yeah.
I think having human in the loop is very important, and that's something we should think about. But I'll also talk about the leaderboard thing. One thing I know in the vision community, so I'm all for creating these kinds of evaluation mechanisms. You really need them, and they need to align with our understanding of the time of what are the problems with the existing systems. But I also very, very strongly want us every 3 years to revisit these things, because what happens is you just have papers upon papers producing tables of comparisons with all of these metrics, and often they drift apart from the problem you're actually trying to solve over time. So not only do we need to create sort of these evaluation metrics, but we need to guarantee that every 3 years we revisit all of them. Otherwise, you end up optimizing the wrong thing. And that's I see that a lot in different subdomains in the vision community, which Jitendra, you can comment on this, and I get tired of seeing the tables of numbers without actually improving the understanding of the problem.
Yeah, after a while, your success at the benchmark is just success at the benchmark.
Exactly.
But this highlights something that 2 of the speakers, Tengyu and Tatsu Hashimoto, referred to, that it's actually a mystery why these models are learning so much anyway, because all you're doing is minimizing the cross entropy or prediction loss. So why do they pick up this other knowledge, and how do we quantify that? So until we have that, we cannot really have a systematic way to design. I mean, we can do trial and error, but until then, we have no way to design.
Any last thought on that topic? Well, I guess everyone said their piece and we're hit 2:30. So I think there's more questions I would have loved to ask, but I'm afraid we've come to the end of this time for this panel. And so we'll call it there, and I'll hand it back to Percy to wrap up the first day.
Thank you.
All right, thanks, Chris, for leading that really lively discussion. And thanks to all our speakers and panelists today. I just want to reflect a little bit on what we covered today. We covered a lot of ground, and it's one thing that struck me is how the issues of risks and social harms showed up in basically every session. This is something absolutely that everyone should be thinking about. And of course, we'll discuss it more intensely in session 4 tomorrow. I do also want to stress that foundation models is fundamentally not specific to language. It's about self-supervised learning on data, and that data can be curated, multimodal, grounded from simulation or interaction. So a lot of these axes are kind of orthogonal. But it will be interesting to see how they will fare in vision and robotics, given the impact and what we've seen in NLP so far. And especially in the last session where grounding, interaction, and physics have been brought up as really fundamental to progress. Also, it's pretty clear that foundation models have problems. I think every single speaker mentioned something either technical or social. And I think a big question is how we react to this. Do we take steps to improve the data or the architecture, essentially staying with the paradigm, or do we need a kind of a bigger reset? So on that note, I'll leave you to think about that question, and I'll see you tomorrow at 9:30 Pacific for session 3 on industry and applications.